Yeah, welcome to Lecture 8. Today we're going to talk about forces on submerged surfaces. So it's the first, I guess, real-world application of in mechanical engineering of this course. So we're going to talk about forces on things like the dam in this picture. So um, being able to integrate the hydrostatic forces along bodies and how we can do that analytically, and we're going to do that numerically as well. So I think it's going to be an interesting lecture. But just a review to start off of the points we did last lecture. So we talked about Pascal's law, which is that within the same connected fluid, 2 points at equal heights will have equal pressure. So we can use that to jump around fluid, like in the manometer problem there. Specifically, Pascal's law allows us to avoid going around the black path here. So we did like a manometer problem. In the gray fluid, we can jump directly from here to here. Once we compute the pressure here, we know by Pascal's law, the pressure at that point is the same because they're at the same height. And yeah, last lecture was all about manometry, which is simply put, you can measure the change in height of a fluid. Say you apply a pressure to a fluid, that fluid can change height. You measure that change in height, you can directly calculate the pressure that was applied to it. So that's how we use manometry. Context again, we're still talking about hydrostatics. It's kind of the last lecture. We're going to do a bit of it on Friday. So a reminder, there's a makeup lecture at 8:30 on Friday. So there's going to be 2 lectures on Friday. So yeah, Friday is going to be interesting as well. But today we're going to talk still within the realm of hydrostatics, more on the application side. So the learning objectives are to be able to create free body diagrams of submerged bodies, submerged surfaces, to be able to construct a coordinate system for integrating pressure along a submerged surface, and to be able to use that coordinate system and evaluate those integrals using 2 different methods. So analytical methods, that's the sort of thing you'd have to do on, for example, a midterm or in the tutorial tomorrow, integrating by hand, functions that you can integrate by hand. But more generally, I also want to present a method you can use to do numerical integration of forces on submerged bodies. So that's more practically what you can do. So the thing that makes us jump between the 2 methods is not all surfaces are these nice like straight lines that we're going to be able to use analytical methods for. For example, the dam in that picture was a pretty complex surface. So in general, you would use numerical integration to compute hydrostatic force on that. Okay, so we'll begin the notes. Before I begin, so yeah, I guess, so there is that makeup lecture on Friday. Any other questions about course administration or content? No? Okay. The second of Friday's lectures, I'm going to give a little feedback survey just on how the course is going so far. So I'm going to give about 10 minutes in that lecture, and I'll bring a printout that I'll have you guys just fill out. It's just anonymous, just if you have any like requests of things you want me to do differently or things that I'm doing that are working really well. So that'll be the second lecture on Friday. So please plan to attend that one. Okay. So the main question we're going to answer today is how do we compute the force on something due to pressure? So something here is just some sort of general object, surface, body, whatever you want to call it. So I'm going to just briefly recall a very important property of pressure, and that's the pressure force at a surface So recall the pressure force is always normal to a surface. So I'm going to give an example surface here. So let's say this diver is our thing we want to compute the pressure force on. So what I'm going to do is examine, say here, a very small element, a very small area on the surface we're trying to compute. So I'm going to enlarge that just to show here. So that's the surface. That's what it looks like. So this, in general, this surface will have area dA. There, the D just means that it's a small surface. So like you could just call it A if you wanted to, but dA is to remind ourselves that we're looking at a differential. So the pressure force on this surface will be, of course, normal to this surface. I'll call that dF. So d small f there. And the normal vector of this surface will be like that. So the normal vector, the uninormal vector, is a unit vector that points outwards from the surface. Let me zoom in just to clarify. So that normal vector points outwards. It's exactly orthogonal to the surface element dA. We know that the pressure force tends to sort of compress the surface. So the pressure force points downwards into the surface. Let's start off by trying to determine the magnitude and direction of the pressure force on this small surface. So dF is an infinitesimal surface force. So it has magnitude because the definition of pressure is just this equation. So the magnitude is just going to be the force is pressure times area. So what that means is dF is the pressure on that element times the area, which is dA. So that's the magnitude of that force. But the direction, force is a vector, so it has magnitude and direction. We determine the direction of this force using the normal vector, the uninormal vector on the surface. And the direction of that force is minus n hat. So n hat is the uninormal vector. So say the surface, say we look at like a 2D kind of snapshot of the surface. Say our uninormal vector is like that. We know that the force will be pushing into the surface. So that's the reason for the negative sign. So you might recall from calculus class that the uninormal vector points outward of a surface. So that's good. We can basically get kind of a line that's orthogonal to the surface now using that uninormal vector. We know our pressure acts into the surface. So the direction is just given by minus n. So that means dF is equal to minus p dA times n hat. So all this is force is pressure times area. Then we multiply this by that uninormal vector, and we've turned it into a vector now. Are there any questions on the calculation of dF there? No? Okay. So now, to compute the total net force, we add up all the dFs over this entire surface. So the forces experienced by every single little element on the surface. the df's, the plural of df. So that's all we're doing, okay? So there's going to be a calculus alert here, but we're just adding up all the df's all over the surface, okay? So the net force, we're going to call that big F. That is going to be the area integral of little df. So that's equal to the integral over the entire area of the body. I'm going to pull the minus sign out. Okay, what's it? So P n hat dA. So that's an area integral. So the area integral means we are just going to add up using calculus the contribution of the four small forces on each of the individual surface elements. That's all this area integral is. So this is more of a concept. So very rarely can we actually evaluate this integral analytically. So that's more of a, you can think of it as more of a, yeah, a concept. So it's going to be an area integral of the local force. So let's talk about methods that we have to compute this integral. For some cases, we can actually do this analytically. Two is computer. I should mention, so these are two methods to compute that force due to pressure on a body. We actually haven't done any hydrostatics yet, so this is a general force due to pressure integral. So even if that pressure is not hydrostatic in origin, you can still compute the force due to pressure on something using this integral. We're starting to look at this now in hydrostatics because we're actually able to compute that pressure through hydrostatics. So this, we haven't actually done the hydrostatics portion of this yet. So are there any questions about this area integral? Okay, I'll give you a systematic approach now to do this analytically, which is what you'll be doing tomorrow in the tutorial. That was the practice on homework 2, so some analytical versions of these integrals. That's the sort of thing you do on an exam as well. I'll give you the systematic way that you can solve these problems by hand, but I'm also going to show later on in the lecture how we can solve this using a computer. So the first thing we'll talk about, and I'll give an example of these analytical methods. So just like I'm sure probably the majority of other mechanics classes, we start with a free body diagram. We define a surface coordinate system. We're going to call our two, the integrals you're going to do are going to be 2D. So we have two coordinates that we need for our coordinate system. We'll call that S hat S and N hat. So those are our two unit vectors for our surface. So N hat is the normal vector like we already saw, but S hat is kind of a tangential vector. So those two vectors are orthogonal. They can make a coordinate system. We'll define our global coordinate system. Which is just our usual I hat, J hat. Then we're going to calculate the differential force or moment due to pressure on a surface element. And then the last step is to use, I guess, the fundamental equations in civil engineering are the summation of forces are zero and the summation of moments are zero with, I'll say, while integrating force. These steps will all become clear. I'm going to do an example. Okay, so example here. So compute the force P required to keep the gate closed. I'm going to assume unit depth into the page. And I'll also give you the density of the fluid and gravity. This is a very, very typical force on a submerged object using the analytical method problem. So we have usually some sort of simple geometry, and we're going to pretend it's a gate, and we want to calculate the forces on that gate. So I'll draw the problem. Say, sort of ground here. We attach a hinged gate. So this is our hinged gate. Assume this is some sort of reservoir or something. So we're going to apply, say we have like a rope or a winch or something. We're going to apply force P at the end of this gate, just to clarify. So this is all filled with water. Again, that little triangle there means there's a free surface at the top of our reservoir. We have air above and air below the gate. Give you the geometry of this gate is 1 meter and 1 meter here. Any questions on the problem setup? So we're going to decide basically on all the problems to work in units of gauge pressure. What that means is we're going to assume in our hydrostatic equation that P0 is 0. Even though the air above and below this gate are at different heights, we'll neglect, because this gate is only 1 meter long by 1 meter tall, we'll neglect the hydrostatic differences in air. The water, though, is quite heavy, so it has a significant hydrostatic gradient down the gate. Okay, so I said step one was free body diagram. So let's do that now. By the way, the unit depth into the page means kind of this way out of the screen. That length is 1 meter as well. Before I just start solving this, are there any questions on the setup? Is anything not clear about this problem setup? Yes, please. Sorry? The hinge is down here. This is this circle thing. So you kind of have like a gate here, and you're kind of pulling on it with a rope or something, and there's just water above the gate. So the water is going to want to push the gate down. Any other questions? Okay. So step one is free body diagram. As you may remember, you can replace the hinge with kind of an x and y force. So I'll call that fxh and fyh, h meaning the hinge. We have a force P at the top. That's the one we're trying to compute. We also have a hydrostatic pressure, which effectively creates a distributed load on this gate. So at the bottom of the gate is deepest, so it will have the highest pressure. And at the top of the gate, we're actually at the free surface, so that pressure will be 0 up there. So this is the force due to pressure on that gate. It's like a distributed load. You might have seen that. You probably saw that before. So there's our free body diagram with our forces. Just to remind ourselves the geometry here. So this would be 45. Just from the geometry of the problem, 1 meter and 1 meter. So now is the point where we're going to start thinking kind of with the end of the problem in mind. So if you had to compute this, say you're doing a mechanics problem in another class, you had to compute the force P here, and you want to skip having to compute the forces at the hinge. You know you would probably take the moment about the hinge because those forces don't have any moment about the hinge. So that's, when you look at the problem, that's where you start. It's good in these problems to begin with the end in mind in that sense. Does that make sense? Any questions about that? So ultimately what we're going to do is take a sum of moments about the hinge in order to do this. We could also do a force balance and compute it that way, but we'd have to account and compute the forces at the hinge. So we do extra steps that way. So step 2 in the algorithm I gave you was to define a surface coordinate system. Here's what I mean by that. So assume that this line here is our surface. Our surface coordinate system will look like this. I'm going to start at the hinge, define the distance along the surface as s. Okay, so if I have some sort of differential element here that I'm trying to compute, the distance from the hinge is going to be s, and the distance from the free surface will be y. The overall length of this will be some length L, which we can compute as just root 2 because we know how long this is. Any questions on the surface coordinate system here? Step 3 is this a global coordinate system? So the point of the global coordinate system is just for things like to define our forces, the directions, but there's usually nothing special there. 9 times out of 10 it's just like up is y and left and right is x. Okay, so now we're going to do the hydrostatics part. So the differential force, in this case I've thought ahead. I'm going to do a moment calculation, so I'm going to calculate a differential moment. So for some element here at a distance s from the hinge, the force on that element will be PA. The area of this element, we'll call the length of that element ds, meaning that it's a small differential element along our s coordinate direction. So PA is going to be the pressure on that element times the area is ds times 1. So that's the unit depth. Assume the unit depth into the page. So the geometry of S, I'm going to erase this, but just to make this clear, so this is some differential element, ds, but into the page, something like that. So that distance there is 1. That's what the unit depth means. I'm kind of just looking at it from that point of view here. So I'm looking at it head on. So that's why the area is ds times 1. Now the pressure at ds, we're able to calculate now the pressure in a fluid based on the depth. So we have to take that s. So the pressure here, the pressure is just going to be rho g y, the way I defined it here. So times ds. I'm going to get rid of the times 1. So the pressure is just rho g y, where again y is the depth from the free surface. We're able to actually calculate what y is from the geometry of this problem. So rho g y is going to be L minus S sine 45. I'll explain why that is here. So this is the overall geometry of our problem. The overall length of this is L. So that's the length of the gate. At some element here, it's a differential element, so I'm just going to make a little point there. I defined S as the distance from the hinge to that differential element. So the length of this triangle is going to be S, and this is 45 degrees. So we've moved S up the gate, and the total length of the gate is L. So that means the remaining part of the gate is L minus S. And in fact, the height, this angle is also 45 degrees in here. So that means that the height of that differential element from the free surface, this is y. Y is L minus S times sine 45. So that's how we compute the pressure, and then we do this times ds. Okay, I'm going to pause here, so please ask. I know you guys have questions, so ask the questions. Yes, Aaron. So S is this distance. And we're trying to compute y. So we're trying to compute this. Yeah. So this is our differential element. It's located here at that point. Yeah. So okay. That answer your question. Any other questions? Yes, please. Yes. So the question was, could you explain what y is? Y is the depth from the free surface. So we know that in a fluid at rest, the pressure is going to be rho gy, where y is the depth from the free surface. I hear lots of chatter, so please, if you guys have questions, yeah, I can answer them too, or you can help each other answer them. Yes, please. Yeah. Y is positive downward. Yeah, that's the coordinate system we defined. So. Oh yeah, you're right. So yeah, I guess in this coordinate system, technically, the way I've defined this coordinate system should be I hat this way, and then J hat would actually be down. So better to be consistent about Y. It's not going to change the computation, but yes, please.
Why did we define S as going that way?
You could define it either way. It might just make the integral, you'll get an exactly equivalent integral if you you're going to see how we do this integration. So we're going to integrate along the length of this. We're going to integrate basically the pressure along the length of this gate. So the way I've defined S, that integration will go from 0 to L. If we had defined S as being from the top of the gate down, then we would have to change the integration to be from like 0 to L again. But you'll get the same answer either way, so don't worry too much about how you define that S. Any other questions? because the math is just going to keep piling on from here. So if you don't understand this setup, um, you'll kind of be lost for the rest of the questions. So that's why I'm making sure that we're good here. Any other questions? So we've computed F, and F is normal to this gate. So that's F of a differential element. So the moment, remember from mechanics, is the force times the moment arm. So can anyone tell me what the moment arm here is for the force F? S. Yes, very good. So the moment arm is just S. So all we're going to do is take our F there and multiply it by S. So rho G L minus S sine 45 times ds times S. This is kind of a magnitude of the moments, so we're going to do the signs when we do our summation of the moments. Any questions on that? So the moment arm is just the perpendicular distance. Since F, we know F is exactly orthogonal to the gate, we don't need to worry about Fx and Fy. We can just say the moment there is going to be F times S. Okay. Step 5 is to do our summation of moments. So I'm going to take the moments about the hinge, and I'll take this sign convention for my moments. So within that sign convention, the moment from our pressure force is going to be a negative. So negative integral of dmh plus that force P. If you remember, just to clarify, the P here is not force P, that's pressure. The P is this force that we're applying that we want to compute. So the moment arm for P is straight horizontal. So the moment arm is going to be that 1 meter. So plus P times 1. That means that P is equal to the integral. I've left this kind of just as a general integral of dmh. So just in terms of notation, these F's and M's that I used here, they probably should have been notated as df and dm because they're differential moments, but I didn't want the notation to get too clogged up for you guys. Yes, Aaron. The H is about the hinge. So I'm calling that hinge H. But I guess it could be hydrostatics too, because that's a hydrostatic moment. Any other questions about this? Okay. So that integral, I'm going to leave the bounds off for now. All I'm going to do is take our dmh. So again, this dm, I'll call this dmh just for clarity here, because I did this moment setup about the hinge, because I'm looking ahead to what we're going to actually need to compute the moment around in order to solve this problem. So I'm going to stick that here in this integral. Rho gl minus s sine 45 ds times s. So the moment balance tells us that this is P times 1, really. So P is equal to the integrated moment from the hydrostatic pressure distribution down this gate. So if we take the moment from a differential element and we integrate that over the whole gate, we'll get the moment about the entire distribution over the gate. Any questions? Because the rest of this is just going to be basically math. Okay. So the balance for this integral, as I suggested before. So this is going to be, I'm going to rearrange a little bit here. The integral from 0 to L. So S is our coordinate. S is not, we don't know S. S is like X or Y. It's just a coordinate in our problem. And that coordinate describes how far we are along the gate. So S equals 0 is we're at the hinge, and S equals L is we're at the end of the gate. So if we integrate the moment from 0 to L, then we get the entire moment about H. So that's going to be the integral from 0 to L of, I'm going to do some rearranging here. So we can pull the rho g sine 45 out of this integral. And L in this problem is root 2. I left it as L because most of these problems are going to be as some sort of integrating along the length of the gate, but we know L in this problem, it's root 2. So this integral is pretty straightforward, so I'm just going to give you the result of this integral. So that gives us around 3.2 kilonewtons. And the direction of P was given in the problem, and it makes sense just kind of given the setup of this problem. Okay, so any questions about that? The setup for all these problems is almost always identical, and it looks something like this. So I'd encourage you to look at the homework 2 before the tutorial tomorrow. You're basically doing this exact same like setup tomorrow to give you guys practice with that. Okay. So now what we're going to move on to is to talk about another way that people can do this analytically. We're not going to use it really that much in the course, but I'm going to use it in the numerical integration part. So it's going to be useful for us that way. Maybe before I move on, is there any questions? I can hear some questions or confusion about this problem. No? Okay. So you might remember from like a statics mechanics course, with distributed loads like that, you can reduce them to a resultant. So in hydrostatics, we have methods to do that as well. So the resultant of the pressure distribution it acts at a point here. So I'm going to make that point red. The point is called the center of pressure. The magnitude of that is PCG, which I'll define, times the area of the whole plate. So that whole plate is area A. So I've drawn it 2D, but the area kind of also includes the width into the page. So PCG is the pressure, say hydrostatic pressure, the area centroid. For a rectangle, for a rectangular gate like the one we just did, the area centroid is just right in the middle of the gate. So that would be like there. So the PCG can easily just be computed as rho gy, if you know where that y is. So it's the depth of the area centroid of that plate. But the resultant force doesn't act through the area centroid, it acts through the center of pressure. So that might be a little bit confusing, but I can give you the formulas to compute the where that acts. So it acts through HCP. So this is CG, that means centroid, and this is CP, the center of pressure. And the distance from the CG to the CP is something that we can calculate. I'm going to call that delta CP. Delta CP is IXX sine theta over YCG. Okay, and I've given this in gauge. There's an assumption of gauge pressure made in this derivation. And then IXX is a moment of inertia. So for a rectangular plate, that's what the moment of inertia is calculated for. So the L, so B is the depth into page. So this is L. So in general, what this method does is you compute a resulting force that acts through the centroid, and then you move it a certain distance away from the centroid. But it doesn't extend, it only extends to very simple shapes, which is why we're not going to spend a lot of time with it. I just wanted you to know that it exists. Also because I'm going to use it in the numerical integration that we're going to do. So So the white textbook 2.5, 2.6 talks about all sorts of different shapes, but we're just going to do the rectangular shape in this class. So now the numerical integration is the second method we talked about, and this is probably more practical one. All the analytical formulas and stuff we were just able to derive where they start getting very complicated when you have an arbitrary geometry. So the force was this area integral here. You can approximate that as the following sum. So say we break that area up into a bunch of different elements, indexed by I. This is kind of how we derived the formula for this integration. We said the total net force is just going to be the sum of all the infinitesimal forces all over this body. Using a computer, we can actually take the body and say break it into 1,000 or however many chunks you want to do, and then compute the pressure at each of those separate points, and then sum them up directly like that. So this avoids having to solve an analytical integral, which we can't do for many real world shapes. So this integration, I will post kind of the formulas that you can use to derive this. you can calculate this if you say you take, maybe I'll give that before I show this. So say we have some sort of curved surface here. Let's approximate this curved surface as a bunch of straight segments like this. So we can calculate now. These are basically, we approximate a curved surface as a bunch of flat plates, which we've done the calculations for. And then you can add up the contributions from all those flat plates to integrate numerically over the surface.